Okay, folks, so I want to get to part 2 of our test and take a look at the answers for that. So on the first page here, we're going to look at questions 26 and 27. Now, both of these are going to be looking at a diagram that represents us looking down at the North Pole. So we can see that the NP, the North Pole here, we can see the sun rays are coming from the left. And this circle around the Earth is going to be the orbit of the moon. And here's the position of the moon. We also have position A. And from this diagram, we can also see that the high tides are located on either side of the Earth in this orientation, and this is called a spring tide. Now, please remember, this is not drawn to scale. Now, what they want to know is, on the diagram below, drag the red X on the moon's orbit to indicate the moon's position when the next spring tide will occur. Well, we talked about the fact that a spring tide is when you have the highest tides, and that's when the sun, the Earth, and the moon are all lined up in a straight line. And so that means the moon would have to move around over to this side. And so if we're looking at this diagram, the moon is right here on the diagram above. And if we wanted to move it around to the other side, the X would have to be somewhere in that location. And then also, question 27. Now we're going to look at that diagram still. And it says, on the diagram below, drag the correct shaded-in portion of the moon that is in darkness as viewed from New York State when the moon is located at position A. All right, so once again, we have our position A. I'm going to get a pen here. And so what we like to do is think about, what are we going to see at this position? Okay, so we're going to look at the moon from this direction. This is our left. This is our right. We would have the moon filled up here, and this would be shaded in on the back side. And so it looks like all of the left-hand side is light, and there's just a sliver of darkness on the right-hand side. So now the options, I obviously don't have those options, so I'm just going to illustrate it. And so it looks like there's just a sliver of darkness on the right-hand side. And so I'll fill that in, and it so was the option that looked like this. And this is actually called a waxing, or I'm sorry, it's the waning gibbous. So gibbous is more than half lit up that we can see, and waning means getting a little smaller. So this is the waning gibbous, just an FYI. All right, let's take a look at questions number 28 through 30 that go along with this diagram here. So this is a side view, and now our sun rays are coming from the right-hand side. We can see that the orientation of our Earth's axis is at a tilt, and so it's tilting towards the sun. And what we need to do for number 28 is identify the season that's just beginning in the northern hemisphere. So if we drew a line through the equator, this would be the northern hemisphere. And now we are tilted towards the sun. What is the season when Earth is in that position? Well, if we're tilted toward the sun, our angle of insolation is going to be larger, and therefore it's going to be during the summer. But take a look at question 29. State the number of hours of daylight that would be experienced at the North Pole when the Earth is in this position right here. Well, if you take a look at this, if the Earth's just going to rotate on its axis here, the North Pole will never get in darkness. So that means right when summer starts, if you are at the North Pole, the sun will never set. It'll always just kind of move just above the horizon, and so you'll never have the sun set. So how many hours of daylight would that be? That will be 24 hours. So this is the beginning of summer. And the last question here for 30. State the number of hours of daylight that would be experienced at the equator 3 months after the date represented in the diagram. Well, we just said this is the beginning of summer. So that's June 21st. If you want to do 3 months after that, that's going to be September 21st. That will be the autumnal or fall equinox. And now during that day, we have half day of light and a half day of dark, no matter where you are. Now on the equator, it's going to be the same for any other place. So half of 24 hours is going to be 12 hours. All right, let's move on to question number 32 and 33. So here we have a diagram that's a little bit more involved. We can see that we are looking once again down from the North Pole. So the Earth is actually kind of tilted in this angle, the axis. So pretend my pen right here is the axis of the Earth, and it's tilted, so it's moving around in this direction. We have the sun right in the middle, and going around the Earth, we also have the moon around its orbit. So the moon is orbiting around the Earth. So again, the orientation of the axis is like this. So it's pointing away out in this direction to the North Star. Now the question is, the photograph below shows the moon as seen from Earth during a full moon. Identify the letter position of the Earth and the moon when the full moon can be observed, and state the name of the eclipse that could occur at this position. Now remember, an eclipse does not always happen every month because the axis or the plane that the moon is on is 5 degrees off of the plane that the Earth is on. So it doesn't always line up. But let's get back to our question. What's the letter where we could see a full moon? Well, to have a full moon, you need to have the moon, the sun, and the Earth all lined up in a straight line and have the moon on the opposite side of the Earth, the whole side of it lit up that we can see. Now, if we start with A, we can only see a quarter of it on the front there. We can see a little bit more there, but that's still not a full moon. This would be a new moon. And if you are in position D here, the whole half that's lit up, you could see it from Earth at nighttime. So that's position letter D. Now the question, last part of that question was name the type of eclipse. So we can have a solar eclipse or a lunar eclipse. And remember, we talked about that the name of eclipse is talking about what is being covered up. And so in this example here, Earth's shadow would cover up the moon. So that would be a lunar eclipse. And we have that in our definitions for our notes. So lunar meaning the moon, or a moon eclipse you could have written. Now question 32 says identify the northern hemisphere season that's beginning at position A. Well, here's position A. So what we have to do is think about which way the Earth's axis is tilting. And I showed you earlier on that it's tilting off at this direction. So we'll tilt it up here. So if we're tilting away at position D, that's going to be the winter. And then after winter comes spring. So in the northern hemisphere at position A, we will have spring. And finally, question 33 for this page, it says, describe one piece of evidence shown in the diagram that indicates this is a heliocentric model. Well, a heliocentric model shows that all planets orbit around a star or the sun. And in this example, we have the sun in the middle. So we could say that Earth is revolving around the sun. So remember, we're revolving, a revolution is going around it, and so all planets will revolve or orbit around a star. That proves it's a heliocentric model. Helio being the sun for helium, and the centric meaning in the middle. So the sun is in the middle. All right, on our last page for this, we have a picture of the diagram represents the sun's apparent path on the first day of 3 seasons at 43 degrees north latitude. So that's around where we are. We're a little shy of that here in our location in New York State. But what they want us to understand is that these solid lines show the path of the sun as seen by the observer, that person right there. And then these dashed lines down below show the nighttime path of the sun that we cannot see because the Earth rotates away from the sun. So taking a look at this, each one of these dates, we have December 21st, March 21st, June 21st. And we also have our horizon. And this line that's going up is called the position of sun at solar noon. And we've talked about that in part 1 of our video. Remember, solar noon is when the sun is at its highest point in the sky for the day. And after that, it starts setting. So it rises up to the solar noon, and half the time it's spent rising, and half the time it will sink or set after that. Now the question is, on the diagram above, drag the red X to represent solar noon position of the sun as seen by an observer on April 21st. So again, we have our dates of December 21st, March 21st, and June 21st. So we have to think about it. What are the months of the year? January, February, March, April. So the month of April is after March, but then it's also before June. So we have to put our X somewhere between March and June on this. Those are only dates that can really apply. So anywhere between this position here for March and that position there for June will be acceptable. Now, question 35 says, identify the rate of the sun's apparent movement in degrees per hour along the path on December 21st. All right, remember, it's apparent movement because we are actually the ones that are moving, but it looks like the sun is moving from our position. Well, no matter what time of day it is, no matter what day it is, the sun will look like it's moving at 15 degrees per hour. Same thing with all the stars in the sky. Any celestial object will look like it's moving at 15 degrees per hour. And that was directly from our notes as well. Now, question 36. Identify the compass direction toward which the observer's shadow would point at solar noon on March 21st. So here it is, March 21st. Here's our compass directions, north, east, south, west. So the rays come down here, and then your shadow will go directly behind you, and that points towards the north. It actually does not matter which day of the year it is. At solar noon, your shadow will always point north. Now, the last question here says, list the 3 dates shown on the diagram from the least number of nighttime hours to the greatest number of nighttime hours. Well, from the least nighttime, we're going to have to look for which one of these paths has the smallest amount of dotted lines, and the greatest number of hours is the one that has the longest path for the dotted line. And so if we take a look at this, if we look at June, it has the least amount of dotted lines. So the least number of nighttime hours would be June 21st. And the greatest, if we look at December here, the longest amount of darkness, so December 21st. And then in the middle will be March 21st. All right? And so that's how we figured that out. All right, well, those are the answers to part 2. If you have any further questions, please let me know. Good luck, folks.